Good evening. At the end of the last chapter, we were left with the rather bleak realization that all the world's known petroleum reserves are going to be exhausted within the next 30 to 40 years. Given that scenario, what are we going to do to replace that vital energy supply source? One of the leading candidates for replacing the loss of power from fossil-based fuels is nuclear power. Nuclear power was developed shortly after World War II and the development of the atomic bomb, and is used in nuclear power plants to generate electricity. These nuclear power plants began to be built in the early 60s, and quite a number of them were ordered to be built for the next 10 to 20 years. However, as you can see from this graph, in about the mid-1970s, there was a sudden drop-off in the number of power plants that were ordered, and eventually no new power plants were ordered, and only the ones that were already online continued in service. And that has been the case until recently, over the last 20 years. That is, that the same 100 or so nuclear power plants have been handling all of the nuclear power generation over the last 20-some years. That, of course, begs the question of what happened in the mid-1970s to dramatically reduce the demand for nuclear power plants. Well, what happened was something called the 3 Mile Island disaster. 3 Mile Island was the name of a nuclear power plant that was built in Pennsylvania, which had a near accident. The accident did not cause any kind of destruction and had only a minimal amount of radioactive material release. But the fact that a nuclear power reactor could have any kind of accident was enough to scare the heck out of residents and politicians, and as a result, they no longer supported the building of nuclear power plants anywhere near any kind of populated area where they would be needed. So consequently, a lot of contracts that had been put in place were canceled, and no new contracts were ordered for the building of power plants again for the next some 30 years. So what do we do about this? And was that fear reasonable? What we will try to do in this chapter is look at how nuclear power plants operate, what are some of their real issues in terms of their safety, and what is the potential future for nuclear power in the United States. Energy can be generated from nuclear reactions in one of two different ways. The first way is called fission. Fission occurs when a large nucleus of a large atom, such as uranium, is split into two or more pieces, and in the process, a large amount of energy is released. The second process is called fusion, which is pretty much the opposite of fission, in which two small nuclei are fused together to form a bigger nucleus with, again, the production of energy. All the power plants that are currently active in the United States utilize fission as the process by which they generate energy. This is a diagram of a nuclear power plant. On the left-hand side of the diagram, we see something called fuel elements. These are rods which contain the uranium or other radioactive fuel that we discussed in the previous slide. This radioactive fuel then, when it undergoes fission, releases a large amount of energy in the form of heat. This heat then is used to superheat the water that surrounds the fuel elements, and the superheated water then is piped to a secondary set of water tanks, where the superheated water from the nuclear reactor is used to heat new water and turn it into steam. The resulting steam then flows through a series of pipes and through a set of vanes that make up what is called a turbine. That turbine then turns a rod which has a copper coil on it, and that copper coil, when it turns inside a magnetic field, generates electricity, which then goes out onto the grid. The steam, once it passes over the vanes of the turbine, is brought into another area where it is cooled down, and the steam is turned back into water. That water then is pumped back into this holding tank, where it undergoes heating again to turn it back into steam so it can continue through this cycle of both boiling to produce steam and then condensing to produce water. In this way, then, the heat energy of a nuclear reaction, nuclear fission reaction, is used to generate the energy necessary to boil water, which then is used to power a turbo generator, which generates the electricity that we use as a result of the action of the nuclear power plant. Another notable feature about these nuclear power plants is the number of safety elements that are built into them. First of all is the fact that the nuclear material itself that's in these rods never comes into anything else that is eventually exposed to the exterior world. This water, which is exposed to the nuclear material, is entirely self-contained. It's not mixed with any other water involved in the plant. It is merely used to superheat other water, which then is also circulated. Even the cooling water that condenses the steam back into liquid is cooling water that comes from yet a third area called a cooling tower or a lake that's typically associated with most nuclear reactors. So you have three separate, totally separate water circulating systems that are used to keep any radioactive water from ever leaking into any other part of the plant. In addition to that, there is a backup cooling system so that should there ever be a leak in the reactor vessel that allowed this water to come out and cause these rods to overheat, this liquid backup cooling water would quickly fill in and keep the reactor cooled the way it should be so that these rods can never overheat. And then we also have something called control rods, which are used to help control the whole reaction so it never gets out of control. And then all of this is contained within a huge containment building that is meant to keep everything again from being exposed to the environment. So a number of important safety issues have been built into this whole system. So why are people concerned? Well, in the case of the 3 Mile Island, what happened was that there was a leak in the reactor vessel. Water did seep out, and these core fuel elements were exposed to the air and became superheated. But the safety mechanisms kicked in, the backup cooling water came down, and they managed to prevent these fuel rods from overheating. And so this is what we would call a successful failure. The mechanisms that were put in place to deal with an emergency worked. However, by contrast, in a nuclear power plant in a place called Chernobyl in the Soviet Union, they did not have a good set of safety factors built into their plant. And as a result, when they had the same kind of leakage called the loss of coolant accident, or LOCA, the fuel rods overheated and it caused the nuclear reactor to blow up. So the public perception isn't remembered by the fact that the 3 Mile Island disaster was averted and never became a disaster. What they remember is that places like Chernobyl and most recently in Japan with the Fukushima plant did occur. And this reasonably causes concern for a lot of people. Now, whether or not the concern is warranted enough to prevent nuclear power from ever being a source of power in the United States is, of course, the topic that needs to be debated. So, is there nothing to fear from nuclear power? Well, yes and no. The problem with nuclear power isn't so much the process as it is the waste products that are generated as a result of the process. The waste products of nuclear power are those materials that are produced as a result of the fission of uranium into other elements, some of which are shown here, namely krypton, cesium, and polonium. And the problem with these waste products is that they are also radioactive, just like uranium, but even more so. And these materials are extremely dangerous, and they need to be safely disposed of. But here's the problem with that. The radioactivity of these materials is measured in by something called a half-life. The amount of time it takes for half of the material to radioactively decay into a non-radioactive safe material. And as you can see here, the amount of time that takes is and can be considerable. In the case of krypton, about 10 years. In the case of cesium, 30 years. In the case of plutonium, 24,000 years. The United States officially considers a nuclear material safe after it has gone through about 10 half-lives. In the case of plutonium, 10 half-lives would be essentially 240,000 years, or 250,000 years, in order for this waste product from the process of fission to be safe. The question obviously is, what do you do with something for 250,000 years while you wait for it to become safe? Right now, the only game plan that the United States has for taking care of and storing this material until it can safely decay to a safe level is to bury it under a mountain in Nevada. This picture down here shows you what that site looks like. This is a place called Yucca Mountain, and there is a facility being built at Yucca Mountain which is meant to store the radioactive materials that have been generated in nuclear power plants for the last 40 or 50 years since their beginning. This mountain, it was picked for its geologic stability. Obviously, you don't want to bury radioactive materials in some place that might have an earthquake. And it is an extremely sophisticated facility for taking in these materials, packaging them, making sure that they're in non-leak containers, and storing them away for potentially 250,000 years or more. The cost of doing all this is, of course, extremely high, which we pay in taxes. And then to complicate matters even more, it's taken about 30 years to get the facility to the point where just now it is beginning to be ready to accept nuclear materials. But now people who live in Nevada are beginning to voice opposition to the presence of this facility in their state, and they are threatening to prevent it from ever being used, which would leave the United States having to store all of its extremely toxic and deadly radioactive materials on the sites where they are now, namely around the power plants that generate them. Somehow we have to come up with a national plan to assure the public that we can safely store these materials for that long a period of time, because we really don't have any other alternative for long-term storage of these materials. So then, what is the future of nuclear energy? Well, the holy grail of nuclear energy is something called fusion energy, which, as you recall from earlier in this talk, is the process by which two smaller nuclei are joined together to form a bigger nucleus, and with the concomitant use of energy. You can use this energy in the same way as you do in a fission plant to boil water and generate electricity. But the big advantage of fusion over fission is that it doesn't generate radioactive byproducts and waste materials. And if we can accomplish this, we can safely use nuclear power for probably the rest of human history.